Now that we have a way to generate Taylor series for essentially any function, as long as we can take an unlimited number of derivatives of a function and find some sort of pattern, then we can generate the Taylor series. We're going to learn a pretty nifty shortcut for doing that. And before we can do that, we want to review this concept of geometric series. One of the best. The geometric series are fun because they're so easy to use, right? They're this pattern that's exponential growth or decay. We're starting with an initial term, for example, 1. And we're finding the next term by multiplying by a common ratio. For example, maybe it's r. So we can talk about the first term being 1, the second term being 1 times 3, the third term being 3 times 3, the fourth term, that's not 3 times 3, is it? The fourth term being 9 times 3, etc., right? This is a geometric series. Okay, so that's if a equals 1 and r equals 3. We could write that as the sum from n equals 0 to infinity of a times r to the n, right? When n equals 0, we get 1. When n equals 1, we get 3. When n equals 2, we get 9, etc. And we just keep on going. And the question about whether this series converges or not should be pretty clear. This series diverges for a number of reasons. One is the nth term test, right? The individual terms, the 1, the 3, the 9, the 27, do not converge to 0. In fact, they don't converge to anything. So therefore, if the individual terms don't converge to 0, then for sure the series diverges by the nth term test. But we could also remember some rules about geometric series that we'll talk about in a minute. So let's talk about that now. So instead of multiplying by 3 each time, let's start by multiplying by 1/3, aka dividing by 3. So multiplying 1 times 1/3 gives us 1/3. Multiplying 1/3 times 1/3 gives us 1/9. Multiplying 1/9 by 1/3 gives us 1/27, etc. So this is the same sort of pattern. It's a geometric series where a, in this case, is still 1, but instead of multiplying by 3 each and every time, we're multiplying by 1/3 each and every time. Now, of course, we already know what happens here, right? We know that because the r value is small enough, because these terms are approaching 0, we don't diverge by the nth term test, but in fact we converge, not by the nth term test, of course, because we never converge by the nth term test. That would be silly. But this definitely converges by the geometric series test. What does it converge to? Well, let's ask the question, why does it converge first? Because the absolute value of r, which is equal to 1/3, is less than 1. Right? As long as r is between -1 and +1, then our geometric series converges. Furthermore, we love the geometric series because not only can we easily determine if they converge or not, but we can find the value to which the series converges. Remember that this is equal to s, where s equals a over 1 minus r. Super important equation. A in this case is still 1, and r is still 1/3, so we can say this is 1 over 1 minus 1/3. Well, 1 minus 1/3 is 2/3, so 1 over 2/3, which is 3/2. All right, so it sure seems like if our formulas are to be trusted, and remember, we did prove this once upon a time. We proved this formula using that nifty little expansion technique and then some factoring. If you don't remember that, I suggest you go back and watch the geometric series derivation video because it's amazing. But I won't go through it again. But if we can trust that formula, then we can say that infinite series works out to be 3/2. Now, I like to play around with this stuff in Desmos and kind of see what it looks like when we do some numerical evidence. So, for example, we can take 1 plus 1/3 plus 1/9 plus 1/27, and we can keep on going for a while, and we can just manually build this. That gets a little tedious. So what if we type sum from n equals 0 to infinity? Well, we can't really type in infinity in Desmos. That's not quite that fancy, but let's put in something close to infinity like 100. Obviously not close to infinity, but close enough for our purposes. And if we take a, which is 1, times r, which is 1/3, raised to the n, then we actually get that this equals 1.5. It doesn't really equal 1.5 if we stop at the 101st term, but it's so close that Desmos doesn't know any different. So here's some pretty compelling evidence that in fact that 3/2 that we got over here is correct, because that is 1.5. So what we can do now, and this is where things get really interesting, is we don't let r equal a number, we let r equal a variable. We're going to let r equal just any old x value. So we can say this is 1 plus x plus, well, every time we get to the next term, we have to multiply by x. So we're going to multiply x times x to get x squared. We're going to multiply x squared times x to get x cubed, etc. That gives us a power series, right? A pretty basic power series because our coefficients are just 1. So we can say 1 times x to the n. Of course, for all of these, we could have left out the coefficient 1, but I like to put it there, at least for now. And well, I mean, if we recognize this as a geometric series, then this is also a geometric series that will converge to the value s, provided that, just like we said that this common ratio had to be between -1 and 1, same rule, provided that x has to be between -1 and 1. And in fact, what does that converge to? Maybe we should even put that before the restrictions. So let me slide that over here. And let's use this nifty formula. Super important formula. Again, it's a over 1 minus r. Well, a is still 1. And r, we've replaced r with this continuous variable x, 1 minus x. Fantastic. So this is an amazingly powerful tool that allows us to turn a rational function into a series by simply knowing the geometric series formula. Okay, I wonder if that really works. Let's see if that works. So we'll go back to Desmos and we'll graph the series and we'll graph the rational function and we'll compare them. All right, so let's give that a try. We'll graph the rational function 1 over 1 minus x. Not a very surprising function. Got a vertical asymptote at x equals 1. Got a horizontal asymptote at y equals 0. Now let's go ahead and graph the power series, the sum from n equals 0 to infinity. Again, we can't put in infinity. In fact, I don't even want to put in 100 because that'll potentially crash my computer. But I think that if we go to degree 20, I think that will be significant enough. And our pattern, if you recall, was just 1 times x to the n. So I'll just type in x raised to the n, and we'll see what it comes up with. Now, this green function is a degree 20 polynomial that is essentially, not exactly, but essentially a power series, right? We can't type in infinity here. But take a look at the comparison between the green and the red. If I hide the red and just look at the green, okay, we've got this kind of U-shaped graph that kind of has this almost sharp turn here. It's a polynomial, so it's not a sharp turn, but it's an almost sharp turn. Compare that to the red rational function. You can't even see the red where the green is because it covers it up. Let's hide the green and we can see, aha, yeah, the red is really there. The green follows the red, but not everywhere. Where does the green follow the red? Let's remember that the green follows the red in this interval of convergence. Not only do we know that this power series converges to this rational function, we know that this power series converges to this rational function for this interval of convergence. So we can go ahead and take a look at that if we don't believe ourselves and graph the absolute value of x is less than 1. And we can see that in that shaded region, let me make that opacity less so it's not quite so distracting. In that shaded region, the green and the red match. Okay, maybe not 100% perfectly because we're only going to 20 instead of to infinity. If we were to go to infinity, they would match 100%. But as soon as we leave this interval from -1 to +1, then the rational function goes down here to negative infinity, where our polynomial shoots up to positive infinity. And over here, again, our polynomial shoots off to positive infinity, where our rational function levels off to y equals 0. So outside of that shaded region, they don't match at all. But within that shaded region, they are a perfect match. So this is fantastic. We now have a way of taking a rational function and turning it into a power series and finding its interval of convergence, all just by knowing this one formula right here. Pretty cool. And we don't have to take a whole bunch of derivatives. We don't have to do the ratio test to determine the interval of convergence. All we need is our geometric series formula and the restriction that we know that the absolute value of r has to be between -1 and +1.